Hello everybody, this is a supplemental video for Physics 121. So it's completely optional. If you don't want to watch it, you don't have to, and it won't have any effect on your progress in this course. I decided to make this video because it seemed to me that when I introduced the Millikan oil drop experiment in the last lecture, that there was at least some interest in trying to understand a little bit more about the details of how one determines the charge of an oil droplet from the types of measurements that you can make in the Millikan oil drop experiment. So let me remind you of the experimental setup. We're going to have two plates. They're going to be charged. I'm going to choose to make the top plate negatively charged for the purposes of this drawing, and I'll make the bottom plate positively charged. There's going to be a small hole in the top plate, which I haven't drawn here, but through that small hole in the top plate, you spray some oil droplets, and I'm going to draw just one oil droplet, and I'm going to assume that it has some charge. Again, just for the purposes of this drawing, I'm going to make a choice, and I'm going to choose that charge to be positive. So what's going to happen is that positive charge is going to be repelled from the positive bottom plate, and it will be attracted to the negative top plate. And so if we were to draw a free body diagram, one of the forces on this charge is going to be the electrical force. We haven't discussed it yet, but actually we'll do it this week. The electrical force can be written as the value of the charge of the droplet times an electric field. Our plates are charged with a battery, and so if I make the battery here, so here's the positive terminal, it's connected to the bottom plate, and the negative terminal is connected to the top plate. Again, this is something we'll see later in the course, but we can relate the voltage of the battery to the electric field and the separation between these plates. And so let's suppose that these plates are separated by a distance d. So in that case, the strength of the electric field would be given by the voltage difference across the battery divided by the distance of the plates. And so if we know the voltage of whatever we're using to charge our plates up, and we know the separation distance between the plates, then we can easily determine what that electric field strength is. Okay, so returning to our charged free body diagram, another force acting on our droplet is the gravitational force. And so that's m times g. And then there's one third one that's important. And so let's assume that for the drawing that we're doing, that the electrical force overwhelms the gravitational force. And in that case, the velocity of our droplet would be towards the top. And let's take the up direction to be positive and the down direction to be negative. Okay. So if it's moving up, this droplet is traveling through an atmosphere. So that atmosphere is air, and there's a viscous drag on the droplet due to the air. And so there's a drag force that acts on this droplet, and it's in the direction opposite of the velocity. So I don't want to derive it. In fact, I wouldn't know how to derive it off the top of my head, but the drag force on a spherical oil droplet moving through the air is given by Stoke's law, and that is 6 pi times eta, where eta is the viscosity of the air, times a, which is the radius of the droplet, times v, which is the velocity of the droplet. And because the drag force is opposite to the direction of the velocity, I'm going to put a little negative sign out here. So in fact, maybe I can clean that up a bit. So d is equal to minus 6 pi eta a times the velocity. Okay, good. So with all of that, what we could do is we could write down from Newton's second law that the net force is equal to the mass times the acceleration. And then so we just have to write all the forces. There is, in our drawing, a electrical force in the positive direction, Q times E, and then it's minus mg, and then it's going to be minus 6 pi eta a times v. Okay, so in fact, what I'm going to do is I'm going to drop these vector signs. This is a one-dimensional problem, and so what we'll do is we'll choose the electric field and the velocity to be positive if they're pointing up, as we've drawn them, and negative if they're pointing down. Okay, so what happens is if this droplet is moving up, and let's suppose it starts from rest and accelerates up. As it moves faster and faster, the drag force increases more and more, and it'll increase until there's a balance of these forces, and once the net force is 0, the droplet will continue to move with a constant velocity. And so that's the terminal velocity. And so what I'm going to do is I'm going to say, well, let's suppose that we've reached that terminal velocity. And so I'll put a little subscript t on the velocity to represent terminal velocity. And in that case, the acceleration is going to be 0, and all of these forces sum to 0. Okay. Now, let's just think about the quantities in this expression and things that we know and that we don't know. The charge Q is, we don't know that. That's what we're trying to measure through this experiment. We already established that the electric field could be calculated, so we know that. We know the gravitational acceleration g, but we don't know the mass of the droplet. When we inject these oil droplets into our droplet chamber, they're sprayed out of like a perfume bottle, and they all have different sizes. And so if they all have different sizes, then we don't know the mass, m, so we don't know m, we don't know q. 6 pi is a constant, eta is the viscosity of the air, we could look that up, and the terminal velocity we're going to measure. And so because all the droplets have different sizes, we don't know a. And so there's a bunch of unknowns in this expression, so it's difficult to use in this form. However, we can simplify things a little bit. What we can do is we can express the mass as, let's see, density is mass over volume, so rho is m over v. So I have to be careful. We've already used v for, I don't want to confuse it with voltage, so let me just put mass over volume. And so that means the mass is going to be equal to the density. So express mass, let me rewrite that. Let's use the density rho to eliminate the mass. Okay, so then the mass is density times volume, and if we assume that our oil droplets are spheres, a sphere has a volume of 4/3 pi times the radius cubed, and I'm using a for the radius. Okay, so then if we go back to this expression, I'm going to call this equation 1. Then we could say equation 1 becomes, let's see, QE minus m. So instead of m, I'll write this as 4/3 pi rho a cubed times g minus 6 pi eta a times the terminal velocity is equal to 0. And this is nice because, you know, if we're using, we control the oil we use, so we know the density. And so now, instead of having the 3 unknowns, q, m, and the radius a, now we have only the 2 unknowns, which are the charge q and the radius a. So I'm just going to rearrange equation 1. What I'm going to do is I'm going to solve for the terminal velocity, because that's something that we measure. Okay, and so let's see. I'll do it in a few steps. Let's move the terminal velocity term over to the other side. And so we have 6 pi eta a times the terminal velocity is equal to q times e minus 4/3 pi rho a cubed g. And so if we want to isolate terminal velocity, we'll divide by the 6 pi eta a, and we'll get, let's see, I'm going to write this as q over 6 pi, 6 pi eta times a times the electric field minus 4/3 pi rho a cubed g divided by 6 pi eta a. And then we can do some cancellation here. Cancel the pi. We can cancel one factor of a. And let's see, 4/3 divided by 6 is 4/18, or that's 2/9. And so terminal velocity is q 6 pi eta a times e minus, let's see, 2 rho a squared times g divided by 9 eta. I think that's right. Okay, and so this, I'm going to call this equation 2, and we're going to come back to it. And so you might look at this and say, well, how does that help us actually determine the charge q when we still have two unknowns? We have the unknown charge and we have the unknown radius. So what we're going to do is we're going to be a little bit clever. And so the first thing we're going to do is what we'll do is measure the terminal velocity when E is equal to 0. And so that means we'll just take our battery and we'll just disconnect it. So we apply no voltage to the plates. The plates don't charge up. The electrical force vanishes. And then we have only the gravitational force and the drag force, and that's it. So when E equals 0, the droplet is in free fall. Free fall just means that there's no other force besides the gravitational force and the drag force. And what we'll do is we'll say that the terminal velocity, just to distinguish it, we'll say that becomes what we'll call the free fall velocity. And so from equation 2, what we see is that the free fall velocity is equal to, the first term on the right hand side vanishes because E equals 0. And so it's equal to minus 2 rho a squared g over 9 eta. That makes sense. Then the negative sign makes sense because if the droplet's in free fall, then it's moving towards the bottom plate, so its velocity is down, and we said we were going to choose that as the negative direction, and so we're getting a negative velocity, and so that's good. We can use a measurement of the free fall velocity to determine the droplet radius A. So if we solve equation 2 for A, what we would find is A is equal to, let's see, we'll get a minus 9 eta times the free fall velocity divided by 2 rho g. All of that would be A squared, and then we would take a square root. And so in equation 2, we had two unknowns, the radius A and the charge. What we've managed to do is come up with a way of finding one of those unknowns, the droplet radius. you might be worried about taking the square root with a negative sign in there, but remember the free fall velocity is going to be negative itself, so we have minus the free fall velocity, and so overall everything under the square root sign is positive. And so we'll get we won't run into any problems with that square root. Okay, so we now know the droplet radius. Okay, good. Let's go back to equation 2, and I want to notice something here. Equation 2, the very last term is minus 2 rho a squared g over 9 eta. But that's exactly equal to this thing. So that last term in equation 2 is the free fall velocity. And so what that means is we can re-express equation 2 as terminal velocity is equal to, what was it? It was q over 6 pi eta a, q over 6 pi eta a times the electric field, and then it's minus a bunch of stuff, but all of that was equal to the free fall velocity, and so we get plus the free fall velocity. The negative sign was included in our expression for the free fall velocity. Okay. So the next thing we could try is, next, let's adjust the strength of the electric field such that the terminal velocity becomes 0. Right, we control that electric field, and what we could do is we could change the voltage of our battery or whatever our power source is, and so we keep adjusting that until the droplet just starts levitating. It's not moving up or down. So if we go back to our free body diagram way back at the beginning, what would happen is if the terminal velocity is 0, the drag force will vanish, and we'll have only the electric force and the gravitational force. And what we're going to do is we're going to pick an electric field until Q times E is exactly equal to the gravitational force M times G. And in that case, the forces will balance, the velocity will be 0, and our droplet will be just levitating. So this is i.e. the droplet, the charged droplet, levitates. And specifically, this terminal velocity is going to vanish. And so, let's see, that's equation 2. Let's call this equation 3 then. So in this case, equation 3 becomes, let's see, 0 is equal to Q over 6 pi eta A, and let's call the special electric field where we achieve levitation as E0. Maybe the subscript 0 is representing that the velocity, the terminal velocity, has reached 0, plus this free fall velocity. And so now what we can do is we can solve for Q. So let's see, what would we get? We would get Q over 6 pi eta A is equal to minus the free fall velocity over E0, or Q is equal to minus the free fall velocity over E0 times 6 pi eta A. And we know all of this stuff because in our first step, what we did is we measured the free fall velocity so that we could determine the droplet radius A. And so VF and A are both known. The electric field E naught is something we control. We adjust our voltage until the thing levitates. We take that voltage, divide it by the distance between our two plates, and that's our electric field. 6 pi is obviously just a constant, and 8 is the viscosity of air. That's something we could look up. And so we know all these quantities, and therefore we can determine the droplet charge Q by first measuring the free fall velocity to determine the droplet radius A, and then 2, finding the electric field, that results in levitation to find the value of Q. And if you did this for a whole bunch of droplets, say hundreds of droplets, if you want to imagine that, what you're going to do is find, the result is you're going to find different charges on the different droplets. However, all of the charges will be multiples of some fundamental charge. And that fundamental charge is the charge of a single electron is minus 1.602 times 10 to the minus 19 coulombs. So if a droplet is carrying an extra electron, that will be its charge. If it's carrying 2 extra electrons, it'll be 3.2 times 10 to the minus 16 coulombs with a negative sign. And you'll never get anything in between those two. If a droplet is missing an electron, its charge will be plus 1.6 times 10 to the minus 19. Anyways, all the charges that you will measure, although there'll be different values for different droplets, they'll all be multiples, an integer multiple of this fundamental charge of 1.6 times 10 to the minus 19 coulombs. I want to just go back quickly because we've described one way of finding the charge of the droplet. It involves 2 measurements, a free fall velocity measurement and finding the electric field that causes the charged droplet to levitate. However, if we look at equation 2, I'm going to rewrite this down the page. So let's just rewrite equation 2. So really, here's a second method to find Q. In fact, it's probably, I would say, a better method. So let's just rewrite equation 2. I'm not going to change anything about it. I'm just going to write it down again. So it was the terminal velocity was equal to Q over 6 pi eta A times E. And I'll write it in a funny way. I'm going to go plus minus 2a squared rho G over 9 eta. Okay, and I want to compare this to the equation of a straight line, which is y is equal to a slope times x plus b, an intercept. And so what we can do is we can identify in this equation above that if we say terminal velocity is our y variable, this is the variable that we're going to measure, right? When we do the Millikan oil drop experiment, we watch a droplet move at its terminal velocity. We measure that terminal velocity by measuring the distance it travels in a certain time interval. And we have a grid in our video feed that allows us to measure that traveled distance. And then we have a slope. And so what I'm going to identify as the slope is everything in the brackets here. And so that contains things we don't know. In this case, what we don't know is the charge and the droplet radius. And then we have an x variable. An x variable is something we control. It's like the knob in our experiment. So we have control over this value of x. For us, it's the electric field. By changing the voltage across the plates, I can vary the strength of the electric field between the plates and therefore the electrical force on our droplet. So we have full control over that. And then, the only thing that's left is our intercept. And this is going to be our intercept. In fact, this is the free fall velocity. The intercept, the y-intercept, corresponds to the value of y when x equals 0. And so for us, our x variable is the electric field. If we set the electric field equal to 0, then the only forces acting on our droplet are the gravity and the drag force, and we get the free fall velocity. Okay, and so the other way to determine the value of Q is we can measure the terminal velocity as a function of the electric field strength E. The data will follow a straight line. So if we were to plot that, we would have something like here's our electric field strength, and here's our terminal velocity. We know the free fall velocity is going to be negative, so our y-intercept is going to be something like this. We could have, well, in fact, we would be able to apply negative electric fields and positive electric fields. And our data would look something like this, and maybe there's some error bars on these data, right? This. And then what we could do is we could fit a straight line through our data, and we could find the slope and the intercept of that straight line. And so what we're going to do is find the slope and intercept of the line through our data. The intercept, B, is equal to, as we know, minus 2a squared rho g over 9 eta. And so we can solve for a, and a is going to be equal to minus 9 eta b over 2 rho g square root. Again, our intercept is the free fall velocity, and it's negative, and so that means minus b is overall positive, and so we get some positive value for the radius. The slope is going to be equal to q over 6 pi eta a, q over 6 pi, pi, 6 pi eta a. And so therefore, if we want to find the charge, it would be 6 pi eta a times the slope. And the value of a that we would have to use would be the value that we obtained from the intercept. And so once we've made a determination of that slope and that intercept, we have everything we need to know to find both the radius and the charge of the droplet. Okay, good. So that's what I want to show you. I just want to show you this video once more that I showed, I think, during the class. I want to show a video. Okay. And so it's a 5-minute video. We won't watch the whole thing, but we're going to track the droplet that was inside that circle. here's the grid that we can use to measure distances. And what is happening now is the voltage across the plates is being adjusted. And at the moment, I'm just adjusting that to change the position of the droplet. And so the droplet we're looking at is the one that's moving inside the row of squares that is second from the right. And so this is 500 volts, and the thing is rising, and here's minus 500 volts, and it's falling. And so we could measure those two terminal velocities at plus and minus 500 volts. That would be 2 points on our linear plot. And so we're going to adjust the voltage again, and just move the position of this thing around. So I think the next voltage where we'll make a measurement is at plus 400. And so we can determine a terminal velocity at plus 400 and minus 400. And this goes on. And so it does plus and minus 300, plus and minus 200, plus and minus 100. And then at the end is 0 volts, which is that free fall velocity. One thing I'll just point out, just remind you of, is that the microscope that's used to look at this droplet actually inverts the image. And so when you see this droplet in this video going towards the top of the screen, it's actually falling towards the bottom plate. And when you see the droplet moving towards the bottom of the screen, it's rising towards the top plate. So that's just something to keep in mind, because I'm going to show you the free fall. And in the free fall, you'll see the droplet rising to the top of the screen. Okay, so I'm just going to advance this video. And so once we've done that, we could make a plot with 11 points at voltages of plus minus 500, 400, 300, 200, 100. That's 10 points. And then free fall, a voltage of 0 would be our 11th point. We could plot that data, terminal velocity versus electric field, where the electric field is the voltage divided by the distance between the plates. And we could find the slope and intercept and get the radius and charge of the droplet. And in fact, that's what's done. Okay, here we are actually at minus 102 volts. And if you look at the droplet, it's just levitating. It's going to sit here for a minute or so, and it's not going to perceptibly rise or fall. And so that means it's levitating. And so what we could do is we could take this 102 volts, divide it by the distance between the plates, which is 5 millimeters for this apparatus. That's the electric field E0 that causes this thing to levitate. And so in that first method, before we talked about the method with the straight line, the first method to find Q needed this electric field to cause the droplet to levitate. And here it is. It's at about a minus 102 volts. Okay, and then I'm just going to advance this a little bit. And here's plus 102 volts. And then I'm just going to turn the voltage off. And the droplet will be in its free fall. And so again, it's moving towards the top of the screen, which corresponds to the bottom plate of the droplet chamber. And so it is indeed falling, and we could measure that free fall velocity. That free fall velocity itself could be used to find the droplet radius, and the electric field at levitation could then be used to find the charge of the droplet if you already know the radius. All right, good. Thanks very much. That's what I wanted to show you, and that's where I'll stop.